Lab. Today we're going to be talking about a few different ways of handling categorical predictors and regressions.
Yeah. So just to kind of do an overview of what we'll be talking about during this lab. So we'll be practicing 3 different ways of examining categorical predictors in a regression framework. We'll start off with dummy coding, which is a really common way to code your categorical variables. And then we'll just talk about effect coding and then orthogonal polynomial contrast to assess nonlinearity within your models. And I want us to note that all of our outcome variables in this are continuous in each of these examples. So to start off, we'll go ahead and load up our libraries. So for this, we'll be using no new libraries. We'll be using the tidyverse library, the LSRR library, and the psych package as well. And the data set we'll be using is one that I think you are all quite familiar with, which is the sleep data set. We've used this in previous labs before. So we'll be using our standard read_CSV function and saving it into a new object called sleep. And we'll be using this for parts 1 and 2 of our demo, and for parts 3 of the demo, where we'll be talking about orthogonal contrast, we'll be using a different data set. So keep that in mind as we go through this.
So for these first 2 parts in this data, we're going to ask the same research question in a slightly different way. So we're going to look at how condition, if you recall, there are 3 different condition levels, sex, identifying as male or female sex, and then how the interaction between the 2 predict sleep hygiene. And so first we're going to walk through how we do this with dummy coding, and then we'll do effect coding. And you'll see that these 2 methods are really similar, but there's a slight difference in the interpretation and the coding, and that ends up being pretty important.
All right, so let's go ahead and get started with our dummy coding example. So keep this separate from effect coding as we go through our examples. So let's start off talking about what dummy coding is and why we use it. So this really is an extremely common approach to working with categorical predictors in psychology. And we use categorical predictors quite often in psychology. Think about this in terms of experimental conditions. You might have 3 conditions that you had participants run through. Well, we need to dummy code those variables in order to run any sort of analysis on them through a regression framework. So dummy coding allows you to compare these mean differences between different levels of a categorical variable. So what we do is we're essentially turning our variables into binomial variables where the effect level of the level of the variable is coded as either a 1 or a 0. And you can specify any of these levels of the variables to a reference group. So the reference group will always be coded as a 0, and your treatment levels will have a 1 to indicate whether it's treatment 1, treatment 2, or whatever treatment you decide. Additionally, we create these new dummy-coded binary variables for any comparisons that we want to make between the 2 groups. And I think that'll be a little bit more clear in the next slides when we show you kind of what they actually look like in your data set. And you only need to use dummy coding if you have more than 2 levels of a categorical predictor. So things like, sex, when there's male and female only binary indicator in your variable, those are usually kind of dummy coded for you actually when they're in a 0 and 1 format. Whereas things where we have 3 treatment levels, we'll oftentimes need to actually go and dummy code those variables. So continuing on, so for dummy coding, as I mentioned before, we'll be converting these categorical variables into a series of binary variables. And this table below kind of shows you what that looks like. So one example of a categorical variable is actually race. So if we have 4 races, Hispanic, Asian, African American, and white, we can see how we have to dummy code our variables. So for Hispanic, you put a 1 to indicate your new variable on the first column. And Asian would be on the second column, and then African American, you'd have a 1 to indicate the third column, whereas white would be our reference category in this case, in which is a 0 across all columns. Oh, okay, and I'll let Gemma take this.
So how we actually code this out in R is we're going to use the mutate function that we've used a few times here. And if you remember, we used the if-else function. I'll show you up here with my mouse, where you put the test expression. Basically, if this is true, then it equals x. If this expression is false, then it equals y. And so how we coded that here for the dummy coding, so we showed you for sex as well, but just walking through, so we have our mutate function, our data frame. The new variable sex is equal to if else. If sex is equal to 1, then the variable is going to be 0. And if sex is not equal to 1, then it'll equal to 1. And so for these levels, 0 is male and 1 is female. We named it just for a little bit easier interpretation in the model. It's a little bit more complicated when we have more than 2 levels. For example, in condition, we have 3 conditions. So we show if else, if condition equals 2, then that's going to be assigned to 1. And if not, it's going to be assigned to 0. For condition equals 3, if condition is equal to 3, that variable will be coded as 1, and if not, as 0. And so what we've really done is we've created 2 new variables. We took one variable that had 3 levels and we created 2 binary variables. So condition 2 is coded as 1 and condition 1 is coded as 0. So this variable will let us compare the difference between conditions 2 and condition 1. For condition 3, we have the third level coded as 1 and the first level coded as 0. This will let us compare the differences between conditions 3 and 1. And so in both cases here, like Neil said, you can choose what reference group you want to use in dummy coding. And here it's the lowest level, condition 1. So this model won't let us test differences between groups 2 and 3, just between 2 and 1 and 3 and 1.
And so we're going to be starting with a simpler model in which we'll be using hygiene as our outcome variable, and we'll be regressing hygiene onto our new dummy coded variables for condition 2 and condition 3. And as you can see, it's actually a pretty simple methodology where it doesn't look too different than your standard regression models. All we're doing is plugging in our newly dummy coded variables, so condition 2 and condition 3, and adding them into our model. In this case, we'll be comparing, as Gemma said earlier, condition 2 to condition 1 and condition 3 to condition 1 on their differences in hygiene levels, which is our outcome variable. So we're keeping it simple for now. We're not including sex or an interaction term for sex to start with, just so we can kind of go and walk through what each of these dummy coded variables mean and how we can interpret their coefficients. Mm-hmm. So, as you can see, we used our OLS regress to view our model output, and we're seeing an R squared of 0.397. So our conditions are explaining 39.7% of the variance in hygiene overall. This model is overall significant, so we can go down and interpret our betas. So let's go ahead and talk about what the intercept is. So in this model, where we only have condition 2 and condition 3 dummy coded, the intercept is the predicted sleep hygiene score when all x variables are 0. So what does that mean? Well, when all x variables are 0, that's equivalent to condition 1, because that's when your dummy codes are all at 0. So really, we've seen that the condition 1 mean hygiene score is 4.66. Now, when we go and look at our beta values, we can talk about condition 2 to start with. So remember, we're only comparing condition 2 to condition 1. So condition 2 is the predicted difference in the sleep hygiene scores between participants in condition 2 as compared to condition 1. Now I want you to notice that I'm not making any comparisons between condition 2 and condition 3. We only are able to make the comparison with condition 1. So really, it's the difference between condition 2 and condition 1. In this case, that difference is 1.627. And then we can go to our last beta coefficient, which is condition 3, which is essentially the predicted difference in sleep hygiene scores between participants in condition 3 compared to condition 1, which happens to be 2.374 in this case. And as we can see, all of our coefficients are significant at an alpha value of 0.05.
And one thing I'll just add is, so this model doesn't test the difference between condition 2 and 3. We could test that if we wanted to. It would just be going back, recoding the variables to change which one is 1 and which one is 0. So that's a simple step that you can add if you really want to look at all of the different relations between your variables and levels.
Great.
All right, so now we're going to make it a little bit more complicated. Back to our initial research question, we don't just want to look at condition predicting hygiene. We also want to know how sex and the interaction between sex and condition are predicting sleep hygiene. So we add those to our model. This should look familiar based on the interactions we've done before. So we have our outcome variable, we have our binary predictor for sex, we have our 2 binary condition dummy-coded variables. And then for dummy-coded interactions, we had 2 terms, one for each level of condition comparison that we're going to be making.
Sorry. So
no,
yeah, we weren't quite sure who to start. I guess I'll go and you can jump in if you want to, Gemma.
Cool.
So as you can see, we run our model. It looks fairly similar to what we were talking about to our last model. However, this time we need to talk about it in terms of simple slopes because we have interactions incorporated in this. So let's go ahead and start off with our intercept overall. So the intercept overall is the predicted sleep hygiene score when all of your x variables are 0. So you have to think about what this means when all of your x variables are 0. So when the sex.f variable is coded as 0, that indicates that it's a male. And when the condition variable is coded at 0, our dummy coded condition variable is coded at 0, that means that it's condition 1. So we have to say our intercept is specifically the sleep hygiene score for males that are coded are males in condition 1 specifically, and that's significant at our alpha of 0.05. Now, these are we gave you some really lengthy interpretations to each of these variables that we'll encourage you to look at on the actual slides itself, the PDF version of the slides. So we're not going to read through these in complete detail, but keep in mind that each of these are simple slopes. And we can talk about these in terms of, we'll talk about a few of them. I mean, Gemma, do you know which ones we should probably talk about specifically with them?
Maybe just the difference between the individual dummy-coded variables and the interactions. So for con2 and con3, the dummy-coded condition variables, again, it's a simple slope because they're involved in the interaction. And so what we're saying is this is the effect of being in condition, that's dummy-coded, so condition 2 for the con2 variable, the effect of being in that condition among males. So when the other x value, sex, is equal to 0, which is males. And so it's basically the difference in the outcome variable for males in condition 2 compared to condition 1. So we're taking the same thing we had in the last model, condition 2 compared to condition 1, but we're adding in that this is the difference for males specifically because sex is in the model. Same thing for condition 3. When the other x value is equal to 0, so when we're looking at males, it's the expected difference in condition 3 compared to condition 1. And so the interaction terms are where it gets a little bit more complicated. So this is the differential effect of being in condition 2 compared to condition 1 for females compared to males. When you have an interaction between 2 categorical predictors, basically you have 2 different levels of comparison that you're making. And something that's cool that you'll see in these is that, so this is going to give us the difference for females compared to males. If you wanted to then calculate what we had for condition 2 and 3, the difference between condition 2 and condition 1 for females, instead of just for males, you can calculate that by taking this interaction term and adding it to the term above. So it is confusing. I encourage you to walk through it slowly. But just to break it down a little bit more, so condition 2 is saying this is the expected difference and sleep hygiene for males between condition 2 and condition 1. The interaction term here, if we add negative 0.63 to 0.2084, which we have over here is equal to 1.411, 1.411 is the expected difference between condition 2 and condition 1 for females.
Mm-hmm.
So the interaction term is the difference between males and females for that initial comparison that we made.
Right. Right. All right, so we're going to go ahead and move on to what effect coding is, and we can talk about what is the point of effect coding and kind of the benefits you gain from effect coding overall. Mm-hmm. So let's start. So what is effect coding and why would we use it? So it is very similar to dummy coding, except now you're comparing one level of a categorical to the mean of all the levels. Previously with dummy coding, you're comparing one level to another, to a reference category level. Mm-hmm. So these are a little bit different way of looking at it. So let's talk about the questions that you're asking. So instead of asking, are two conditions different from each other, like you were in the dummy coding, the effect coding asks something a little bit different, in which we're asking, is this condition different from the average of the overall of all the conditions, or of all of the coded variables? So keep in mind, we'll be saying that the rule in dummy coding is that values can only fall in 0 and 1. The rules for effect coding is that all of the values in your new variable are going to sum to 0. And I think once you start kind of putting this together, it'll make a little bit more sense as well. Mm-hmm. So let's go ahead and start by talking about specifying the effect coded variables. So again, we're utilizing our mutate function, and we're creating a new variable, a few new variables. We'll start with our condition2.ec, which stands for condition2 effect coded. We utilize our if-else statement, and it looks just like dummy coding to start off with, right? So we are using if-else condition equals 2, where condition equals 2, mm-hmm. Then it takes on a value of 1, else it takes on a value of a 0, and then a similar coding for condition3.ec. Now, the only difference now is we need to specify those variables in which it takes on condition 1. And what we're going to be doing is replacing the areas where it would be 0 across the entire row in which the condition equals 1 and filling that in with a negative 1. So what do? We actually rewrite over our condition2.ec variable using our if-else statement again, in which case we say when condition is equal to 1, turn it into a negative 1. And this is going to be where the real difference between our effect coding and our dummy coding comes in. Now it's equal to negative 1. And if it doesn't, is where, I'm sorry about that, let me restart. Condition equals 1 and it comes to negative 1. And then you have it equal to condition2.ec. So overall, what we're doing with this line of code is turning in our, any time it's equal to condition 1, it'll turn into a negative 1. So what I'll encourage you to do is actually write down this code, get it to run, and then actually look at your data set to see where the negative 1 values fill in. Mm-hmm. All right. And then you'll do the same thing for condition 3. So again, with condition 3, you overwrite your condition3.ec variable, use the if-else statement, where condition is equal to 1, you fill it in with a negative 1, else, comma, it'll keep the same as condition3.ec. So any cases where it's condition 3, it'll remain a 1. Right. Okay, so then we're going to start off with a simple effect-coded model without the interaction or sex terms. So we use the simple, if you look up to the top here, where we are using our LM statement, regressing hygiene on condition2.ec plus condition3.ec, and our data is asleep, and we use our OLS regress function to show it. You'll notice that our R-squared value doesn't change at all from our dummy-coded model if you compare the two. Both of them are explaining 39.7% of the variance. Overall, our model is significant. One of the main differences here is that our slope coefficients now. So to start off, we can look at our intercept. So our intercept in effect coding is the grand mean of the sleep hygiene across all 3 treatment levels. So if you were to take the mean of the conditions for hygiene, you would get a mean value of 5.994. Now, our slope for condition 2.EC is predicted difference in sleep hygiene score between participants in condition 2 compared to the mean of all 3 treatment conditions. So it's really a difference between that intercept and condition 2. So keep in mind with dummy coding originally, we are comparing that condition 2 value with condition 1. Here we're comparing it with the overall grand mean of them all. And then for condition 3.EC variable, the same thing. This is the predicted difference in sleep hygiene score between participants in condition 3 as compared to the mean of all 3 treatment conditions. Okay. And I'll let Gemma go ahead and take this one.
So again, we're making it more complicated here. We're going to include the same effect coding variables that we used, but here we're adding in another categorical predictor, sex again, and then also the interactions between them. And just a really quick pause that I think Neil mentioned, but I feel like is important when you're really thinking about why would I use this. I think effect coding is really important to know, like, is this condition different than average? As in, if I'm doing a whole bunch of treatments and I don't just want to know if it's better than control or better than another treatment, like, is this particular treatment, like, actually better than most of them? So, in our more complicated model, so here, the intercept is the grand mean of sleep hygiene across all of the conditions again, but only among males. So when the other x value, sex, is equal to 0, so males, it's the grand mean of condition 1, condition 2, and condition 3. And that's 5.433. Sex.f female is our sex variable. And so this, like the dummy coded model, is an interaction. And so it's a simple slope here. It's the predicted difference in the average sleep hygiene between females and males across all the conditions. So essentially the expected difference between males and females in sleep hygiene regardless of whatever condition they were in. Similar to what Neil was saying about, so condition 2, we're comparing condition 2 to the average of all of them. Here it's a simple slope again because this term is in an interaction. And so it's the effect of being in condition 2 compared to the average of all conditions among males specifically. Same thing for condition 3. This beta, condition 3.EC, is the expected difference between condition 3 and the average of all conditions just among males specifically. Now we look at the interaction terms. This is pretty similar to what we did in dummy coding, in that we still, again, have 2 different levels of comparison that we're making when we have an interaction between 2 categorical predictors. In effect coding, though, it's the differential effect of being in condition 2 compared to the grand mean of all conditions for females compared to males. So that double level comparison. And once again, if we wanted to know the difference between being in condition 2 versus average of all conditions for females, we would take the estimate for males, which is 0.402, and we would add negative 0.042. Oops. Sorry about that.
There we go.
And so when we add those 2 together, that gives us the predicted value for being in condition 2 versus average for females specifically, and that's over here, 0.36. And so, same thing as dummy coding. We're starting by making the comparison in these values just among males, and then we can use the interaction term to see how that comparison differs for males versus females. Anything to add, Neil?
No, I think that was great. Cool. Okay. And I would really just encourage you to read through each of these interpretations on the PDF slides so that you can really get a good understanding of what each of these are. We put them in pretty great detail here for you so that you can reference these without us speaking in it as well.
Yeah, this is hard. This is a hard concept to wrap your head around at first. I think at least it was for me. So
Hmm.
I would take it slow and be patient and really like work through it slowly.
Yeah. So now we're going to start talking about orthogonal polynomial contrast, in which we're going to be assessing if if there's any nonlinearity within our models with these variables, and we use kind of a similar method to kind of get at this. So let's talk about what are orthogonal polynomial contrasts, which otherwise known, if you kind of want to do more information seeking on the internet, these are also known as trend contrasts. And why do we use them? So again, like as I was stating in the previous slide, these allow us to evaluate these nonlinear relationships between the categorical predictor and some sort of continuous outcome. Mm-hmm. So with continuous predictors, we can model these by squaring the x to test for a quadratic effect or cubing it within the model. So it would be something like your outcome variable regressed on x plus x squared plus mm-hmm. x cubed in order to assess these effects, in which you just test to see if there's a difference. This is pretty similar to what we're doing, except we're going to be doing this and specifying it through categorical polynomial contrast to test the differences in the effects. So on slide 25 of this, we'll have actually the contrasts that are necessary to test these effects to see these polynomial contrasts and see if you have these differential effects. So keep this in mind, though, that this type of coding system is really only to be used with ordinal variables in which the levels are equally spaced. And you have to think about that just in terms of, well, we actually have different levels, so we'd expect to see a different leveling of effects from level 1 to level 2 because there's actually an increase from one to the next.
Yeah, and just to reiterate, the contrast levels for this, you shouldn't ever need to generate them yourself mm-hmm. unless you want to have a little fun side math project. There are tables that'll give you these, and we'll give you a table later on. So you never have to go through and actually think about how to specify the contrast. You're just going to look at the levels that have already been researched and well established.
Yep. So we want to talk about these effects we can evaluate with more than 3 levels of a categorical predictor. So what does it mean if it's linear, quadratic, or cubic? So really, a linear increase or decrease is really just if we increase the dose level of y, we can select. If we increase the dose levels of x, we can see that y will continue on a linear trend. And this is just your main model where y equals a plus bx, right? So we can select the best level based on this. So as x increases, we expect an increase in y as well. So pretty linear trend. A quadratic trend is really, you remember that parabola that you've seen from a quadratic. So if we increase the dose level of the y values will also be increased until a certain dosage, in which after that the level of dosage will actually have a negative effect. And this is really, if you think back to kind of standard algebra, we can see our kind of standardized equation for this. And then lastly, cubic is a little bit more complicated, but overall, if you look at a graph and you see these kind of trends, you can talk about whether or not these are a cubic effect or not. But a cubic effect is when the dosage would increase y values after a certain dosage and then decrease it. And if we increase it more after a certain while, the dosage levels will begin to increase again. And it's shown by the model in purple. Yeah,
basically linear, no bend in the line, quadratic, one bend in the line, cubic, 2 bends in the line. And then you could test more advanced effects too, if you wanted to, depending on how many levels of the categorical predictor you have.
Yes, it's always 1 minus the number of levels in the categorical predictor you have that you can actually test.
Great.
All right, Gemma, you want to describe the new data set?
Sure. So we're going to read in a different data file for this part of the activity. This one's called Cog Test, courtesy of Kim Henry. This is a study in which people were assigned to spend a certain amount of time practicing a task. This was visual discrimination. And then their score on a cognitive test was measured. And so people were randomly assigned to do either 0 minutes of practice, 2 minutes, 4, and so on until 14 minutes of practice. The two variables are practice and score. And what we're going to do, oh, sorry for that typo, is we're just going to filter it down. So we just have 4 levels of practice, our categorical variable. We could include more, but just for simplicity of this interpretation, we're doing it. And so we're filtering the data. So we're only going to have the data file that includes when practice equals 4, or this bar is or in R, when practice is 4, 8, or 12. And notice that these are all evenly spaced. So we didn't do 0 minutes, 2 minutes, 6 minutes, 14 minutes. We made sure these are evenly spaced, or else the orthogonal polynomial contrast wouldn't work.
Mm-hmm. And so I think the first step is to always visualize the relationship between X and Y when you're doing this, to kind of make an assessment of whether or not you can visually see that there might be a quadratic or cubic trend within your data. Mm-hmm. So we've plotted out our variables using our predictor variable on the x-axis and scores, our outcome variable on the y-axis, mm-hmm. and simply plotted a line that was free to vary across all of our levels there. And, just kind of looking at this graph, we could see that the slope varies across our different levels. So if we look at, level 0, it's very low, and then it kind of has this change in slope from levels 4 to 8, and then from 8 to 12, it has a difference in there. So we're kind of coming to this conclusion, or at least we have evidence to see that this may not necessarily be a linear trend between the two, but we're actually going to go ahead and test that through our orthogonal contrast.
Okay, so this is the table that we mentioned before. This is we have the website down at the bottom. You can find a similar table just by Googling it or looking in different stats books. And just to break it down, so these are the contrasts that you're going to be using, and you'll see we're going to plug these into the next slide. Over here, the number of treatments. So we have 4 different levels of practice. So we're going to be in this section here. If we had included 6 different levels of practice, we'd be down here. We're using 4 here. Now, the number of levels of the categorical predictor will tell you what different effects you can test for. This is the degree of polynomial, so x to the 1 first power, or x squared, or x cubed for a cubic effect. And so if you only have 3 levels, you cannot test a cubic effect. You can only test a quadratic effect. Here we have 4 levels, so we can test x to the first power, x squared, and x cubed. We can test all 3. We cannot test the effect of x to the 4th power.
So now we're going to go ahead and specify our orthogonal polynomial contrast. So I know you see a lot of code here, but it's quite simple if you break it down. What we really did is just put a lot of information into one mutate function. As you can see, we only have one mutate function here, in which case we just specify the mutate function, indicate our data set, which is cog in this case. And we used the contrast from the previous slide for that, where we have 4 treatment conditions to specify our linear contrast, our quadratic contrast, and our cubic contrast in order to talk about this. So you'll notice this, we are creating a new variable called linear to start off with our linear contrast. We use our handy if-else function again, and then we use the practice variable, which is the level of practice that they had. So in this case, for the first line, we're indicating where they had 0 minutes of practice. And we refer to our table from the previous slide to indicate that the contrast that we'll be setting for our first level will be -3. And then we simply, for the first line, we set it back to practice for the else part of our if-else function. Then we go ahead and rewrite, so use a comma, and then indicate that you're rewriting the linear variable by using linear equals, if else, practice equals 4. So this is when they're at the 4 minutes of practice, equals -1. And again, we obtained that from our table from the last slide. And then we'll go ahead and just rewrite our linear variable. So we have anyone who has 4 minutes of practice will receive a -1 on the linear variable. And then we do the same thing for the practice at 8 and the practice at 12, but using 1 and 3 instead. Now, again, referring back to our table, we're going to create a new variable called quadratic, where we're going to test the orthogonal polynomial contrast for our quadratic statements to see if there's a quadratic effect. So again, we use our quadratic equals if else, practice is equal to 0, we indicated a 1, which can be seen from the last slide, and then just indicate it so that it'll equal to practice if it doesn't meet that criteria. Then again, quadratic equals if else, practice equals 4 minutes, we turn it to a -1. If it doesn't meet that criteria, it stays as quadratic, as we're indicating here. And then again, the same thing for those at 8 minutes, where we indicate it at a -1, and then those at 12 minutes, where we indicate it as a 1. Lastly, we're going to use the cubic effect to look to see if there's a cubic effect, in which case we use from the table again, where practice equals 0, this is going to turn into a -1. If practice is equal to 4, we turn the cubic into a 3. And then if else turns to, when practice is at 8, we set it to a -3. And when practice is at 12, we set cubic to 1. And these are all, again, and I can kind of just switch back to the previous slide. If you look at that highlighted number there, this is exactly where we got our numbers from to indicate what our contrasts are overall. So again, the linear contrast is specifying if we're seeing a linear effect. The quadratic variable is specifying contrast to test if there's a quadratic effect. And then lastly, of course, the cubic contrast is going to test to see whether we have a cubic effect. And what we'll be doing in the next set of slides is just plugging these into regression models to test for a significance in that effect.
Just like Neil suggested when we coded the other variables, you can just open your data frame and just take a look at how these things coded and make sure that it all looks right. Make sure that your mutate worked.
Mm-hmm.
All right. So this first model, we are using the linear variable we made as our predictor and regressing score onto that. And this we're interpreting just like we would any simple linear regression. In terms of, is the linear effect significant? So we're not looking at, like for a 1 unit increase in X, it's looking at, is the linear effect explaining a lot? And so here, our model fit statistics are pretty good. We're explaining 90.9% of the variance in the outcome. Our standardized regression estimate of 0.95 is a pretty large effect size, and the overall model is significant. So it fits pretty well. However, since we looked at our data and visualized it, and we saw that there could be a potential curved relationship, there might be a better way to examine this. So, what we'll do next is we're also going to test the quadratic effect. And how we do this is we simply just add quadratic and as another predictor in the model. And when we do that, when we add the quadratic term, now we're explaining 98% of the variance. That's a 7.1% increase, which is pretty big. And the quadratic term is statistically significant. So what that's telling us is that this relationship has a bend to it. There's a curve. And so we need to maintain the quadratic term in the model. I can go.
Yeah, just continue on.
So next, we're going to test for the cubic effect. Basically, this is going to say, so we know there's at least one bend in the model. Is there a second bend in the model? And we can test for that because we have 4 levels of the categorical predictor. So just as before, now we're just adding cubic, that variable we made, into the model. And what we're seeing here, so first of all, our R-squared doesn't increase at all. We're not explaining any more variance in the model by adding the cubic effect. And the cubic term itself is not significant. And so this is saying there's not a second bend to the relationship, so there's no evidence for a cubic effect. So here we'd conclude that the quadratic trend is the one that best fits these data, and that's the model that we would use and report on.
Mm-hmm. And we went ahead and gave you some additional resources on categorical variable coding systems. Some of these include, how to dummy code your variables and the differences between dummy coding and effect coding. We also provided you some links about the polynomial contrast as well, and kind of indicating where that table that we mentioned earlier, where like how to code these variables and what is the purpose of coding these variables if you wanted to kind of dive deeper into more information about these overall contrast statements that we had you form today. So just, go ahead and look at the PDF version of the slide and just click through these links, and you can get a kind of more in-depth knowledge of all of these, the dummy coding contrast, the effect coding contrast, and the polynomial orthogonal contrast as well.
Mm-hmm. All right. Let us know if you have any questions. Hope you're all doing well.
All right. Thanks, everybody.